You ever have that moment you're using an AI agent, it's supposed to be brilliant, it aces all the tests, and then it just completely faceplants on a super simple real world task? Yeah, it's a huge frustration in the AI world, and it's the exact problem the team behind the M2 project decided to tackle. So let's get into why this keeps happening and what they figured out. And this quote from the M2 team, man, it just hits the nail on the head, doesn't it? It just perfectly captures that huge gap between how a model looks on paper and how it actually works in practice. I mean, if you've worked with LLMs, you know this feeling deep in your bones. Okay, so this slide just lays out the whole conflict perfectly. On one side, you've got benchmark brilliance. This is where the model is just crushing the leaderboards, solving these incredibly complex, but let's be honest, totally made up problems. And then on the other side, you get real-world failure. The same model gets totally lost trying to use a new tool or just follow a basic instruction. This is the gap, right? This is the chasm M2 was trying to cross. So to actually bridge that gap, the team realized they were juggling two kind of conflicting goals. And really, understanding these two goals gets right to the heart of what it even means to build a useful AI agent right now. Okay, so first, they absolutely had to crush it on the benchmarks. And look, this isn't just about bragging rights, right? It's about proving the model has solid foundational skills. But the second goal, that's the real prize, actually generalizing to the real world. Because let's be real, all those benchmark skills are pretty much useless if they don't actually work for you, the user, out in the wild. So pretty early on, the M2 team just hit this frustrating wall. Their models were smart, for sure, but they just weren't adaptable. And that roadblock led them to their first huge breakthrough. And it was all about changing how an agent should fundamentally think. They came up with this idea called interleaved thinking. And this is a really powerful concept. The idea is, instead of the agent making one big plan at the very beginning of a task and then just trying to follow it, its internal monologue, its thinking, happens continuously. It's woven in between every single action it takes. So, the process looks something like this. First, the agent thinks about what it needs to do. Then it acts. It actually does something. It then observes the result of that action. And then, and this is the absolute key, it thinks again. It reevaluates its whole plan based on this new information. It's this constant think, act, observe, think loop. Now, why is this approach such a game changer? Well, for two big reasons. First, it helps the agent stay on track during really long, complex tasks. But way more importantly, it lets the agent adapt to what the team calls perturbations. All the random, unpredictable changes and errors that the real world just loves to throw at you. This constant thinking process is what gives it resilience. But, a new way of thinking wasn't the whole story. This actually led them to their second major discovery, which was all about how an agent should fundamentally adapt to its environment. So the team's first idea was pretty straightforward. Hey, if you want an agent to generalize, just teach it more and more tools. Scale up the tool set. And you know what? At first, it totally worked. Their scores in the benchmarks shot up. But they pretty quickly realized they were solving the wrong problem. The model was super brittle. You change the environment just a tiny bit, and its performance would just crater. And that led to this profound realization. True generalization isn't just about adding more tools. It's about being able to adapt to perturbations, those unexpected changes, across the agent's entire operational space. It's not about knowing more things. It's about being resilient to change in every single part of the task. And these perturbations can pop up from literally anywhere. The tools available to the agent might change, right? The system prompt could be totally different. The user might phrase their request in a weird way. The environment itself, we're talking files, APIs, that could shift. And hey, even the response you get back from a tool might not be what you expected. That old tool scaling idea, it only addressed that very first item on this list. That's it. All right, so to power this brand new level of thinking and adaptability, the team had to make a really fundamental and, a somewhat controversial engineering choice about the model's core architecture. And this was the question the community kept asking them. Why on earth would you choose older, slower tech like Full Attention when there are all these shiny, new, efficient alternatives out there? Well, their decision really came down to just being pragmatic.
I mean, sure, those efficient attention models looked great on simple benchmarks, but the team found they had these kind of hidden weaknesses in complex reasoning. And they realized the real bottleneck wasn't designing the architecture, it was evaluating it. It is incredibly hard to know if a model is actually good, and they found these efficient methods could hide subtle but really critical flaws.
And this quote just sums up their whole philosophy perfectly. A useless model is useless even if it's free. You know, quality is just non-negotiable. If the model can't do its core job reliably, then who cares how fast or cheap it is? Everything has to be built on that foundation of quality.
Okay, so you've got an agent that can think and adapt, powered by a quality-first architecture. So what do you feed it? And that brings us to maybe the most foundational piece of the puzzle, the training data. Their first principle here, the quality of the model's reasoning, its chain of thought, is absolutely non-negotiable. The internal logic has to be complete, has to make sense. What they found was that if the thinking is too brief or shallow, the models start skipping steps or getting way too confident, which, as you can imagine, is a complete disaster for performance.
Second, and this one's kind of counterintuitive, they discovered that harder, more complex queries are actually better for training. It might seem backwards, right? But pushing the model with really difficult problems is what forges truly robust and flexible reasoning skills.
And finally, diversity is everything. Think about it. A model that's only trained on code and math will be great at code and math. Shocker. But to build a truly general agent, you've got to feed it data from tons of different domains. Logic, science, following instructions, even creative stuff, because each one of those teaches a totally different way of thinking. So to just quickly recap their best practices for data, make sure the reasoning is logically complete. Mix up the response formats to keep the model on its toes. Be absolutely ruthless about cleaning out bad data, hallucinations, errors, got them out. Prioritize the harder queries, and once you've nailed the quality, then you scale it up with more high-quality, diverse data. So the whole journey of the M2 project really leaves us with these incredibly powerful lessons. The real benchmark is just, does it work in the real world? And to get there, an agent has to think continuously. It has to be built to survive constant change. It has to put quality above everything else. And it has to be fed a diet of amazing, diverse, and difficult data. And all of that leaves us with one final and I think really crucial question. If we know that leaderboards and benchmarks don't really tell the whole story, that they're a leaky abstraction for what an agent can really do, then how should we be measuring progress? I mean, what does a truly useful and robust AI agent actually look like to you?